Alright, welcome to lesson 3. Here we're going to look at some AP free response questions that involve real-world scenarios and rates of change other than position, velocity, and acceleration relationships. Let's go ahead and get started. Alright, so here's the first question that we're going to do. Go ahead and copy down this question. I know it seems like quite a bit of work, but we're only going to do this question. We'll do that one together, and then you'll do one more on your own. So think of it as a worthwhile investment of your time. Copy it down, work through it first on your own, give yourself 15 minutes of work, and then when you've finished, go ahead and draw a horizontal line through your paper and press play, and we'll take a look at it together, and you can take some extra notes on how the solutions should look. Alright, so as we read through the introduction, there are some key pieces of information here, and while I can obviously underline those and sort of visualize this situation in my head, I think this is one of those situations where it is very helpful to draw a little sketch of the situation, in this case the blood vessel, just to make sure that we don't sort of lose sight of what we're dealing with here. So the first thing that I have is a blood vessel that is 360 millimeters long, and it's circular at every point along the way, but those circles vary in diameter. So let's go ahead and draw a quick picture. Here we have it, and notice a couple of key things. Obviously I have the total length of the blood vessel, but I've also drawn it so that I can see that the diameter is varying as I move across, and I'm just going to go from right to left. I think that makes the most sense here. And so the diameter at any point x along the way is going to be given by this function b of x, where x represents the distance from one end of the blood vessel, and b of x is twice differentiable and represents the diameter at that point. So if we just consider x to be any point along the way, then the diameter is going to be this right here, the diameter of that circular slice of the blood vessel at that instant, and we can label that diameter to be b of x. So I can label that, and then the last piece of information, sometimes we'll just sort of slide by, but is really important. B of x is twice differentiable, and what this means is that b prime and b double prime exist. And more so, if b is differentiable, that means that b is continuous. And since b prime is differentiable, because I was able to get b double prime, that means b prime is also continuous. And this is kind of that valuable information that separates scores of 8 and 9 from scores of 5 and 6 and 7. So you'll want to get used to picking up on this and just writing it down. While it seems innocuous at the beginning, when you're on part D over here and you're sort of grasping for pieces of information, it will be really nice to look back at your notes and see that there. Alright, so now that I've got all this information down, I'm ready to go ahead and hit the problems. One thing I want to note here is how much work I've done before even looking at any of the problems. And it seems like it's taking a lot of time, but that time is actually going to save you time when you're solving the problems. And the more work you do up front, the less work and the less thought you're going to have to put in to each of these pieces here, and really the less time you're going to spend on these problems. So while at first it will really increase the time it takes you, trust and have faith that at some point it's going to start working to your advantage. Alright, part A is pretty straightforward. I want to write an integral expression, so I'm going to have an integral here, that in terms of b of x, and that represents the average radius of the blood vessel over the length of the blood vessel from 0 to 360. So there's two components. The first is that I need an expression that represents the radius in terms of b of x, and then I need to find the average value of that expression over the course of the length of the blood vessel from 0 to 360. So the first component, I need something that represents the radius at any point x, and that's not too bad because the radius is half the diameter, and since b of x represents the diameter at any point x, I simply multiply by 1/2. So now the average value of the radius I can find by taking the average value of this expression over the course of the length of the blood vessel. And I can find the average value using the definite integral. So that means that my average value of the radius will look something like this, where you'll note, of course, that I am just simply applying the definition for the average value of a function, and the function that I want the average value of is the function that gives me the radius at any point x, which is 1/2 b of x. I can simplify this a little further. I can factor out the 1/2. 1/2 times 1/360th is going to be 1/720, and so my final expression will look like this. And it may not seem like factoring out the 1/2 is quite that big a deal, but it's always nice to make the expression as simple as possible because there's a decent chance that we'll be approximating or finding the value of this expression later on. And sure enough, that's what happens in Part B. So Part B says approximate the value of your answer from Part A using the data from the table and a midpoint Riemann sum with 3 subintervals of equal length. And we want to show the computations that led to our answer. So because we have written this nice and simple, I can see very clearly what I'm going to do. To approximate this value, I have 1/720 times this definite integral. And I can approximate the value of this definite integral using the midpoint Riemann sum with the data that I'm given in my table. So the next thing I need to do is actually make sure I have my intervals set, and then I can go ahead and write out my computations that I will make. So looking here, I can see I need 3 subintervals of equal length, and so I'm going from 0 to 360. So if I just split that up into 3 subintervals of equal length, 360 divided by 3 is 120. So each subinterval is going to go a length of 120, so I have 0 to 120, 120 to 240, and 240 to 360. And sure enough, it works out that there is a point that is in the middle of those subintervals that I have a value for, right? They're not going to ask you to compute Riemann sum without giving you the data that is necessary. So now I can go ahead and write out my Riemann sum, and it will look like this. Notice that I have factored out the 120, which is the length of all the subintervals. So 120 times 30 is the value of the area of the first rectangle, 120 times 30 is the area of the second, and 120 times 24 is the area of the third. And then multiplying this all out, I'm going to end up with 14. And remember, this is the approximation for the average value of the radius. So this is in millimeters. And just to check and make sure that this makes sense, remember the radius is 14 on average. That would make the average diameter 28. And so if I'm looking at my data here for the diameter, it seems to make a lot of sense that the average value of my diameter is 28. Part C looks a little daunting at first, and we're actually going in the next unit to take a look at these situations a little more in depth. And so when you see a situation like this on your actual AP test, it won't quite look as daunting. But it's a great example of how you can actually just take a look at a definite integral and pick apart the different pieces that are going on within it and use that to understand what the integral is computing. So that's exactly what we're going to do. We're going to take this term by term, really think about what it represents with respect to the blood vessel, and try and use all the parts of this to make sense of what exactly this is computing here. Okay? So let's start from the inside and work our way out. That's usually the best place to start. So looking at this integral, let's think about what b of x divided by 2 represents. Remember, this is simply the value of the radius at any point x along our blood vessel. So this is simply the radius squared. The radius squared. Now, what do you know that is very common in geometry and that involves the radius squared? Well, what you should think about is the area of a circle. The area of a circle is the radius squared times pi. Do we have a pi hanging out anywhere? We do. It's been factored out, but that doesn't mean that I can't factor it back in. It's a constant, so I can either bring it outside or move it in. So let's rewrite our integral with pi factored in and with r of x in place of b of x over 2, since those are the same thing. Now that we have our definite integral written in this way, it's very easy to see what each part of this product represents. And when we visualize it and write down exactly what it represents, it'll be very clear what our definite integral is going to be summing up from 125 to 275. So pi times r of x squared at any point x is simply going to give you the area of the circular cross-section at that point x. Now, the key to recognizing the true meaning of this expression is going to be combining the meaning of the area of the cross-section with the meaning of dx in the context of the situation. Since we think of dx as an infinitesimally small change in x, and x represents the length along my blood vessel, what I'm doing is I'm multiplying the area of this cross-section by this very, very small length. So let's just draw that out and see if we can, that visual can really tell us what this whole expression is representing. Now, dx can be represented with this very small width here, and I'm going to draw it a little bigger than it might actually look, right, so that we can visualize it. Okay, that's dx. And so what that's doing is that's multiplying this area along this width. So there's going to be all these paper-thin areas of pi r of x squared along this width. And so that will end up looking like this. And so what I can see is that what this really is the volume of this very thin slice of my blood vessel. Okay? And just to confirm that, note that dx is millimeters and pi r of x squared is millimeters squared because the radius is millimeters, so I have millimeters times millimeters. So this will be an area in millimeters squared. And when I multiply by dx, which is in millimeters as well, I'll get a volume which is in millimeters cubed. So the meaning of this definite integral, if I add up these volumes from 125 to 275, I'm going to get the volume of my blood vessel from x equals 125 to x equals 275. And so writing out my answer, I would say this integral represents the volume in millimeters cubed from a position of x equals 125 millimeters to x equals 275 millimeters along the blood vessel. Right, part D says, explain why there must be at least one value x such that b double prime is equal to 0. So not too hard to figure out what I'm trying to find. The tricky part is coming up with a plan to show that this has to be the case at least once. All right, think about this. B double prime is the derivative of B prime. Okay? And so what we're showing is that the rate at which B prime is changing at some point has to be 0. And when you think of theorems that tell you something about an instantaneous rate of change, you want to think first and foremost about the mean value theorem. The mean value theorem says that if you can show that the average rate of change on an interval is some value, then at some point on that interval, the instantaneous rate of change will have that exact value, as long as my function is continuous. Well, B prime is continuous. So if I can show that the average rate of change of B prime on an interval is 0, that means that on that interval somewhere, there has to be a place where its instantaneous rate of change, B double prime, is equal to 0. So now, how are we going to find some values of B prime? Well, we can use the same exact method. We can use the mean value theorem, right? Because what we can do is we know some values of B. So since B is continuous, if we apply the mean value theorem to our function B, then if we have an average rate of change for B, we know that on that interval, B prime has to take on that value. And since we need to show that the rate of change for B prime is 0 at some point, we're going to be looking for two intervals where B prime has to have the same value. Well, let's make it easy on ourselves. Let's see if we can find any intervals that will show us that b prime has to be 0 on that interval. In other words, an interval where the average rate of change for b of x is 0, and then find another interval where it's 0 again. So if you notice, from 60 to 180, the diameter has not changed. So the average rate of change on this interval is 0. Mean value theorem states that means b prime has to equal 0 at some point on this interval. Okay, let's look for another interval. If I go to 240 and 360, I notice again the average rate of change is 0, meaning that b prime again has to be 0 on this interval. So I have b prime being 0 somewhere here, b prime being 0 somewhere here, and so the average rate of change of b prime between those 2 points is going to be 0 as well, meaning that b double prime has to be equal to 0 at that point. So let's write that up. Okay, so here it is. Let's walk through it one more time. This can be tough to grasp, but it is a super valuable concept to have in the bag. So we apply the mean value theorem to b of x, because it's continuous, we can do that, on the interval from 60 to 180. And since the average rate of change is 0, this implies that b prime of c sub 1 is equal to 0 for some c sub 1 in that open interval from 60 to 180. Right? So I know b prime is 0 at some point on this interval, and then I'm looking to show that it's 0 again on some other interval. So similarly, on the interval from 240 to 360, the mean value theorem implies that b prime of c sub 2, some different point, is equal to 0 for some c sub 2 in the interval from 240 to 360. So these are my 2 points, c sub 1 and c sub 2. It doesn't matter what they are, it just matters that they exist. So there are 2 separate points where b prime is equal to 0. And so now I can apply the mean value theorem to b prime on the interval from c sub 1 to c sub 2. Again, it doesn't matter what they are. I know c sub 1 is between these 2 values and c sub 2 is between these 2 values. So c sub 2 is greater than c sub 1. And since b prime is continuous, the mean value theorem implies that the instantaneous rate of change of b prime, in other words, b double prime, will be equal to the average rate of change on that interval for some value c. So the average rate of change on that interval is simply b prime of c sub 2 minus b prime of c sub 1. Both of these are 0, so we have 0 over c sub 2 minus c sub 1, which is 0, for some c in that interval. In other words, b double prime of c has to equal 0 at some point in between c sub 1 and c sub 2. And therefore, b double prime of x equals 0 at some x between 0 and 360. So notice here that I'm applying the mean value theorem twice. Both times I have to make sure that the function is continuous. I know b is continuous, I know b prime is continuous, so I can apply the mean value theorem to both of those functions, and they will tell me that the average rate of change will be equal to the instantaneous rate of change of that function at some point on any interval. All right, super tricky one, but as I said, really well worth it to go over it and understand it. Come by and ask some questions if you still have some. All right, let's go ahead and take a look at another question for you to try on your own and bring into class. All right, appropriately, Camp Newton, not Cam Newton, but Camp Newton. Go ahead and copy this question down and then set a timer for 15 minutes and see how far you can get in 15 minutes. Don't worry about finishing in 15 minutes. Simply note where you are, so take your time, and then go ahead and finish the question out on your own, and we'll take a look at the scoring tomorrow. Again, 15 minutes doesn't matter. What matters is that you get the question right, so take as long as you need.